Okay, here's our fourth example, and it shows two powers, and they have different bases. This is where logarithms really come in and help us out, because the different bases would be extremely difficult to work with otherwise. I've got 4 raised to x plus 3, and this is set equal to 3 equal to the negative x power, and we want to know is there a value of x that can make this equation true. Well, we're going to invoke the power of logarithms right off the bat. Because they're different bases, we're just going to right off the bat take a log base 10, a common log of both sides. So we're going to say the log of 4 to the x plus 3 is equal to the log 3 to the negative x. And taking the common log of both sides gives us some options. For instance, we can now use our exponent rule and take this x plus 3 and move it out to be a coefficient of the log of 4. This negative x can then be a coefficient of the log of 3. So we'll do a little rewriting here. This is x plus 3 times the log of 4 is equal to negative x times the log of 3. Hopefully things are looking a whole lot simpler already. I'm going to do a little reverse distribution. I've got the log base 4 being multiplied by this binomial x plus 3. So I'm just going to multiply x times the log of 4 and 3 times the log of 4. And we're going to get x log 4 plus 3 log 4 is equal to negative x log 3. Okay, I'm going to do two things in the next step. I think you can handle it because otherwise I'm probably going to run out of paper down here. I'm going to subtract this 3 log 4 from both sides. So it's going to become a negative 3 log 4 over on the right side. And I'm going to add an x log 3 to both sides. It'll become a positive x log 3 over here. All I'm doing is just subtracting this one, moving it over here, moving this term over here, kind of swapping them around. They'll change their signs in the process. And what I want you to realize is the reason I'm doing this is that I want both the terms that have an x in them to be by themselves on one side of the equation, because then we're going to factor that x back out. So when I'm done doing this little switcheroo, I'm going to have x log 4 plus the x log 3 is equal to negative 3 log 4. Okay, now I've got an x here and an x here. That's a common factor. I can factor the x back out. X times log 4 plus log 3 is equal to negative 3 log 4. Take a deep breath. We are almost there. All I have to do now is divide out this log 4 plus log 3. So if I divide it on this side, I got to divide it on this side. I'm going to end up that x is nothing more than negative 3 times the log of 4 divided by log 4 plus log 3. This is the exact answer. This is what we call, if you want the absolutely algebraic precise answer, it doesn't get any more precise than this. If you want a decimal equivalent that's approximately equal to the correct amount, you're going to have to put it in your calculator and let your calculator kind of crunch this out. And it's going to be a long decimal, most likely irrational. And x will be approximately equal to 1.6737. It may extend quite a bit depending on your calculator, but this should be enough decimal precision that if you plug, this is a negative. If you plug this number back into this equation up here, you should find that they come out very, very close to the same amount on both sides of the equation. And that's example number 4.